Today on Macaulay Math, we're optimizing functions and finding Extrema. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200 Calculus 1, Lesson 13 on optimizing functions and Extrema. Our goals for today. We will find extrema of a function on an interval. We will find the relative extrema of a function on an open or closed interval, and we will optimize functions. A practical use of the derivative is to use it to find a maximum or minimum of a function, its optimum values. This is accomplished by finding extrema. In previous courses, we used technology to find extrema. But by using calculus, it is possible to find extrema on any interval algebraically. So let's talk about some definitions. Number one, f of c is a maximum of f on the interval I when the value for f of c is greater than any other value for x, for all x in I. And number two, f of c is a minimum of f on I when f of c is always going to be less than f of x for any other x in I. Minimums and maximums of a function on a given interval are extrema or extreme values, the absolute or sometimes known as the global maximum or the absolute global minimum are extrema of the entire function. Note, odd degree functions have no global extrema, and that is because you're always going to have some value that's going up towards positive infinity or down towards negative infinity. And endpoint extrema can occur on the endpoint of an interval. Another definition, a relative extrema, maximums and minimums occur at a maximum or a minimum point of an open interval of a given function. Extrema are extreme points, either high or low relative to the points arbitrarily close to the extrema. And in pre-calculus, we use technology to find these points. So let's take a look at a quick Desmos demonstration here. I have this simple function, f of x equals x to the third minus 6x. And this is a third degree polynomial. And so we can see that this thing is going to have no global extrema because it's always going to go down to the left and it's always going to go up to the right. So there are no absolute extreme values on this, but there are some relative extrema. And so this point right here, relative to the points generally close to it, it is the highest value. And this point right here, generally close to the points near to it, is the lowest value. A critical number is a value for x where the derivative of the function is either 0 or the function is not defined. And the reason that we will find critical numbers is there are some results that we get from finding critical numbers. And the first one is where the extrema may be located. They are places where functions can change from increasing to decreasing. The places where the horizontal tangent line can exist. And these are places where the functions are optimized either in maximums or minimums. If we go back to this Desmos, we can see right here is going to be a point where it changes from increasing to decreasing. There'll be a horizontal tangent line at that point, and it will also maximize this function in this general vicinity. Same with this minimum here. It is a place where it changes from decreasing to increasing. There'll be a horizontal tangent line, and it is the minimum value relative to the points in that general vicinity. All right, so how do we find a extrema on a closed interval? To find the critical numbers of a function, f on a closed interval from a to b, so not a real number line graph like we saw in this demonstration here. This is all of the values. We're talking on just a closed interval now. I'm going to find the critical numbers of f on a to b, and then we're going to evaluate each critical number on a to b, and then we're going to also evaluate the endpoints at a and b, and then at least the least And number 4, the least of the values found in number 2 and number 3 is a minimum, and the greatest value is going to be a maximum. So let's look at some graphs to try and understand these points just a little bit better. Okay, so let's look at this example. Consider the following graphs. Do they have an absolute maximum or minimum over the closed interval a to b? All right, so the closed interval is going to include both a and b in this particular instance. So I've got some gaps and I've got some holes here. I actually, on this graph, have a hole at a and I have a hole at b. And there is a non-removable discontinuity here somewhere in the middle. And so in this particular instance, because there is no highest value, there is no global maximum. But because there is an absolute lowest value, and we can find that value, this is the global minimum. This one here, and again we have opens at the end and we have an open here at the bottom, and even though that value exists, we cannot say what the actual absolute minimum is. So this graph has no global extrema. Okay, so for this example, we're going to find the absolute extrema of the function over the closed interval. So we have this function from f of x is equal to 2x over x squared plus 1, and we're going to find the extrema over the closed interval, -2 to +2. So we're going to follow the steps, and the guidelines for finding extrema over a closed interval. First thing we want to do is we want to find the critical numbers of f on a and b, and so that is going to be the places where the first derivative is either undefined or equal to 0. So we need to find the first derivative. So we're going to go f prime of x, and this is a quotient, so it needs a quotient rule. So we're going to go Hody high. We're going to take that bottom piece of the function and we're going to rewrite it. So x squared plus 1, and then the derivative of the top, so that's just going to be 2. And then from that, we're going to subtract, and it'll be high d ho, so we will leave the top alone. And then we will multiply that by the derivative of the bottom. So the derivative of x squared is going to be 2x, and then the derivative of 1 will just be 1, all over the denominator squared. So x squared plus 1 quantity squared. And so let's simplify this a little bit. F prime of x is going to be, let's see here, we'll distribute, so we'll have 2x squared plus 2 minus 4x squared all over x squared plus 1 quantity squared. And then I'll have the 2x squared minus the 4x squared will simplify down to 2 minus 2x squared all over x squared plus 1 quantity squared. Now the denominator is never going to be 0, so we're never going to have it undefined. So here's what we're going to do. We're going to set the numerator equal to 0. Because for a fraction to be 0, the numerator has to be 0. So if I go 2 minus 2x squared and I set that equal to 0, we'll subtract 2 from both sides. That'll give me negative 2x squared equal to negative 2, x squared equal to 1, x equal to plus or minus just 1. And here we're dividing by negative 2, and then we will take the square root. So my critical numbers here are x equals plus or minus 1. All right, so we should go back to our guidelines here. We'll evaluate each critical number on A to B, and then we also want to evaluate the endpoint. So let's go ahead and do that. So we want to find f of the endpoint -2. We want to find f of the -1, f of 1, and then we also want to find f of 2. Okay. So let's do that real quickly here. -2, and I plug it into the original function, I will receive 4/5 out. If I plug in -1, I get -1 out. If I plug in 1, I'll get 1 out. And if I plug in 2, I'll get +4/5 out. So this right here is the minimum value. And that will be at -1, -1. And this will be the maximum value. And that will be at +1, +1. And if we wanted to check that, we could go back to Desmos. All right, and here we see, remember this is a closed interval, so we wouldn't be looking at anything that is less than -2 or bigger than +2. And we can clearly see that the endpoints would not be global maximums or minimums, or even relative maximums or minimums. And we can see that 1, 1, and -1, -1. Let's just zoom in here. 1, 1, and -1, 1 are our extrema. Our next example is a special case. It says here, find the absolute maximum of f. Now, f of x equals x minus absolute value x is a special case because, remember, f of x equaling to 4 minus x is actually a piecewise function. And it is the piecewise function f in this particular instance because it's going to change at 0 because we have no horizontal shift left or right. And since it's the absolute value, it'll be 4 minus x for values of x that are greater than or equal to 0. And then it'll be 4 minus negative x, because we have to make what's inside negative, for values of x that are less than 0. And minus a negative, we will just fix that right here, and we'll make that plus a positive. Get rid of that parenthesis there. And so we know that f is continuous and differentiable. On the two intervals from -infinity to 0, and then from 0 to +infinity, because they are just linear functions, and all lines are both differentiable and continuous. And so we have one spot that is not differentiable. So only x equal to 0 is a critical number. And it's not differentiable at 0 because we have that sharp turn. All right. And so it is a critical number. So it's one of the only places where we could have a absolute maximum or minimum. And we can clearly see that 0, 4 is the global maximum. All right, last example. A sprinkler is constructed in such a way that d theta over dt is a constant, and theta ranges between 45 degrees and 135 degrees. The distance the water traces horizontally is given by x equals v squared times the sine of 2 theta all over 32, where v is the speed of the water as it exits the sprinkler. Find dx over dt and explain why the sprinkler does not water evenly. What part receives the most water? So this particular sprinkler is not one of those spin type sprinklers. I got a picture here. is one of those oscillating sprinklers that goes back and forth, and so it goes over to 45 degrees and then it goes back over to 135 degrees. And the first thing it wants us to do is to find dx over dt. So let's do that. Let's derive with respect to time x equals v squared sine 2 theta over 32. Now, before we do this, we need to note that v squared is a constant. And why is it a constant? It's a constant because it represents the speed at which the water is coming out. So you're not going to be changing that speed. That speed's always going to be the same regardless of the angle that the water is coming out. So we can count that as a constant, which is actually pretty nice because we can rewrite this as d over dt of x equal to, and we'll rewrite it as v squared over 32 times the sine of 2 theta, and we'll think of this as a constant. All right, so the derivative dx over dt is going to be equal to, we leave this constant alone, so v squared over 32. The derivative of sine is cosine. We leave what's inside that cosine expression alone, so the 2d theta. And then we multiply by the derivative of what's inside. So this will be 2 times the derivative of whatever theta is with respect to t. So d theta over dt. Now let's simplify that. The 2 and the 32 will cancel out. So dx over dt will give us a final value of v squared over 16 cosine 2 theta times d theta over dt. That is our dx over dt. That is the first portion that they asked for. They said, find dx over dt. We found that. So now we want to explain why the sprinkler does not water evenly. What part receives the most water? So the most water, we're talking about some sort of optimization here. So we note that d theta over dt is given to be constant. All right, so it's always moving at the same rate. And v squared over 16 is a constant. So we only have to consider the cosine of 2 theta, right? Because that's the only thing that's changing. And we know that cosine has to be between -1 and +1. Those are the only values that can come out of a cosine expression. We have a limit for theta so these would be the endpoints of the possibility, and so we're just looking for critical numbers. Now, because this is calculus, we should change our angles to radians. So recall that 45 degrees is equal to pi over 4, and that 135 degrees is equal to 3 pi over 4. So we want to know a few things about this. We want to know where it's going its fastest and where it's going its slowest. Since this expression right here is essentially dx over dt is the velocity of the point where the water hits the ground. All right. So you've got your sprinkler right here, and at 35 degrees it's shooting there. At one point when it shoots straight up, it's shooting there, and then as it goes to 135 degrees, it shoots there. And so you get this X value that travels down and back and then down and back. All right. So our extreme possibilities for cosine are the cosine of 2 theta equaling to -1, the cosine, let's put parentheses around that, of 2 theta equaling to 0, and the cosine of 2 theta equaling to 1. All right, so cosine equals -1 when that value inside here, which in this case is 2 theta, is equal to pi. And so theta would equal pi over 2. And it equals to 0. Cosine equals to 0 when whatever's inside this expression is equal to pi over 2 or 3 pi over 2. And so theta equals pi over 4 or 3 pi over 4. And cosine equals 1 when what's inside of that expression is equal to, so 2 theta equal to either 0 or 2 pi. Now when I divide, I get theta equals 0 or pi. Now here's the issue. Both 0 and pi are outside the domain that we're given, so we don't even consider those because they're not even in the values. So in this particular instance, the point is moving fastest when theta equals pi over 2. Why? Because when I plug in pi over 2, I'll get a -1. And remember, what is that -1 going to represent? A velocity. The point is moving slowest when theta equals pi over 4 and 3 pi over 4. That's when the velocity slows down to 0. So the grass will get the most wet at the endpoints of the stream, because it'll be sitting there the longest and sitting there the longest, and here it's just going to move real fast. All right there, boys and girls, that is all I have. Let's make that a stream. So the Star Wars fun fact of the day: Boba Fett was introduced in Star Wars The Holiday Special, which included Carrie Fisher singing a Life Day carol and Wookiees wearing clothing, which I always found to be weird. He wore just a bantha strap and a pouch while he was out with humans, but he wears a red gown when he is on his home planet. Well, that's all I got for today, folks. Have a good day. Goodbye.